Well, folks, the stories never end, right? So we said 2023 El Nino was ocean dynamic in the sense heat accumulated and trade wind anomalies were potentially generated from the Indian and Atlantic Ocean warming, and the warm water that's been accumulating spilled over, creating an El Nino. So now you see that El Nino doesn't have such a unique definition. As long as some warm anomaly appears in the tropical Pacific, we can call it El Nino. We say Central Pacific El Nino, Cold Tongue El Nino, or East Pacific El Nino, Extreme El Nino. And remembering that the original name El Nino came from warm waters appearing off the coast of South America. We are now moving a little bit away from that, and El Nino Southern Oscillation is, a coupled mode, but we've said that Southern Oscillation can occur without strong coupling to the ocean with just thermodynamic coupling, and we are saying there are uncoupled El Nino warmings happening as well. So this paper lists some of them and basically points out that these tend to start late and they don't move the deep convection center from the west as much, so the teleconnections are different, and predicting them is a challenge because it's the coupled behavior with the Kelvin waves and the slow evolution, the recharge-discharge are what give it the predictability. Okay, so let's just read a bit just to understand how this occurs. I'm again being very brief. In light of a warming climate, the complexity of the El Nino Southern Oscillation makes its prediction a challenge. In addition to various flavors of El Nino, and so ocean warming in the central and eastern tropical Pacific is not always accompanied by corresponding atmospheric anomalies. That is, the atmosphere and ocean remain uncoupled, no Bjerknes feedback. Such uncoupled warm events as happened in 1979, 2004, 2014, and 2018 are rare and represent an unusual form of ENSO diversity. So they're adding to the CPEP ENSO and extreme ENSO, another form of uncoupled ENSO. Weaker zonal sea surface temperature anomaly gradient across the tropical Pacific compared to a conventional El Nino may partially account for the decoupling or uncoupled behavior. Also, the uncoupled warm events typically start late in the calendar year, which raises the possible influence of seasonality in background conditions for the lack of coupling. So depending on how the upwelling occurs in late summer, early fall, and so on, may begin to play into whether the stochastic forcing can grow into multiplicative noise and become coupled and so on. Okay. Without coupling, the impact of the warming in the central and eastern Pacific is on the without coupling, the impact of the warming in the tropical and eastern tropical Pacific on extratropical climate is different from that of its coupled counterpart, and they look at North America to make this point, which I'm going to skip, but you get the point. In a warming climate, plain language summary says the features of the El Nino Southern Oscillation seem to be changing, so they are attributing these changes to anthropogenic forcing and the related ocean structure changes. For example, during El Nino events in 1979, 2004, 2014, and 2018, oceanic warming in the central and eastern tropical Pacific was not accompanied by corresponding atmospheric anomalies. That is, the atmosphere and ocean remained uncoupled. And remember, 2014 was part of the 2014, 15, 16 El Nino. El Nino was predicted for 2014, but it did get warm, didn't qualify as an El Nino based on the amplitude of the anomaly and the duration, but 2015 became obviously a well-discussed El Nino. These uncoupled warming events were associated with a weaker east-west contrast in sea surface temperature anomaly across the tropical Pacific compared to a conventional El Nino. Also, the uncoupled warm events typically start late in the calendar year, which raises the possible influence of seasonality in the background conditions for the lack of coupling. This obviously same words, but this is meant to be for non-experts. Without coupling, impact of the warming in the central and eastern Pacific on extratropical climate is different different from that of the coupled counterpart or ENSO, leading to different predictability of seasonal to interannual climate in extratropical regions, such as the United States, which has a strong winter signature. So the winter of El Nino year can get a lot of storms on the west coast, and other signatures appear in the southwest, southeast, northeast, and so on. Okay, so let's just quickly look at a few of them. 7980, you can see monthly mean SST in shading and OLR contour anomalies averaged over 5 south, 5 north, which is typical for considering El Nino. So here we are starting from July 79 going down to November 80. So a warm anomaly appears, but the OLR anomaly, which is negative, which means sorry about that. Remember, negative anomalies are stronger deep convection, and the shift towards the east doesn't happen even though there is a warming, and in fact there is a positive anomaly in OLR, which means it's drier than normal anyways, and there isn't much of a signature here going into May 1980 either, but there is a warming. So warming, return to normal or slight cool anomalies, 0 to minus 0.5 or so, and then another little warming, 0 to 0.5. That's 79. 2004, similar behavior, but the warming is now more over towards the date line as opposed to the Central Eastern Pacific here. 14, 15, 14 obviously appeared to want to go into an El Nino. Nothing much happened, and then 15 evolved into a normal El Nino, quite a strong one, in fact, and you can see the OLR negative anomalies and the convection shift happening. 18, 19, again, similar strong convective anomaly around the date line, with warming also a little bit more heavy on the date line, with the warming spreading at a low amplitude towards the East South American coast as well. 82, 83 was a normal El Nino. You can see strong warming with strong convection shift, and now you have the opposite anomalies appearing here, similar to 97, 98, but this one was even stronger. This was also called a double dip El Nino by some people, so you can see that there was warming which peaked in 82, 83, and then in spring of 83 it was still like a second warming. Okay, this one was of course discussed a lot. A very strong deep convection shift with dry negative anomalies in convection and drought and wildfires and so on, dust storms, etc. on the western side over Indonesia, Australia, and so on. Okay, so you're looking at warmings that happen without coupling, as seen in the shift in convection. They don't show the wind anomalies here, but if you put the wind anomalies, you would see the westerly wind bursts going across the dateline into the east in these anomalies, but not in those ones. That's the uncoupled behavior. Okay, looking here at the time series of monthly mean Nino 3.4 and normalized CP OLR, Central Pacific OLR line indices, OLR indices, 79 to December 2019. So going from 79 to 2019, the black line here is the CP OLR. Green bars represent yeah, you get the idea. OLR. So obviously, when you have warmings, you have negative anomalies in OLR. So 79, 80 was here, 82, 83 was here, 86, 87, 91 to 94. There were events. There were tiny things here from 91 to 94, 97, 98. This is 2004, 5, which is counted as CP, and so uncoupled, and 2014-15 uncoupled. You can barely see a signature there, but you can see see those better here when you just look at individual events: 79, 80, 2004, 5, 14, 15. 14, of course, went on to become a big El Nino in 2015, and then the shift of the OLR deep convection happened. 18, 19, again mild with just a slight shift. So it's just emphasizing what we saw as Hofmuller diagrams. Looking here at the wind anomalies, composite of SST and UV thousands of surface winds in vectors. Nino 3.4 is greater than or equal to 0.5, and CPOLR is less than 0, so you should get negative anomalies, and you get the composite warming with coastal signature horseshoe pattern on this side, and you get lead lag correlations between Nino 3.4 and the OLR anomalies, with peaks corresponding to convection shift seen in the OLR. Whereas here you are seeing very strong westerly wind anomalies. Here you are let's make sure composites of monthly mean anomaly of SST and wind at 1000 hectopascal. Nino 3.4 is greater than or equal to 0.5. C. CPOLR less than 0, and in B, Nino 3.4 greater than or equal to 0.5 degrees C, and CPOLR greater than 0, so warming, but you have no convection shift during January 79 to December 29. So they are 2019, sorry. So they are doing the composites of uncoupled El Ninos and coupled El Ninos, and you can see CPOLR is here positive, and U and V gradient. So you are going to look for SST gradients driving hydrostatic pressure gradient and wind anomalies, and you can see the wind anomalies here. Negative basically means easterly, so heading towards the east-west, that's negative. Basically, it argues that the Linson-Negam pressure gradient mechanism can produce wind anomalies in the uncoupled El Ninos, because you still have SST gradient being created. Okay, so so winds are not coupled in the sense of the Bjerknes feedback, but there is some response just due to the SST gradient change. Okay, the uncoupled warming events in which the warming in Nino 3.4 is not accompanied by the corresponding atmospheric anomalies are unusual in the spectrum of ENSO diversity. The hypothesis about the decoupling and tropical Pacific zonal gradient of SST is consistent with the previous work. For example, McFadden and Hu identified, two different papers, identified a regime shift in ENSO variability with a decrease in the amplitude and an increase in the frequency of ENSO since 99-2000. We have argued for a cold state regime shift. There are other papers arguing that this regime shift was associated with the strengthening in the zonal mean climate state contrast between the western and eastern tropical Pacific, and a westward shift of the crucial atmosphere-ocean coupling region. We discussed this in the context of how 24 El Nino and multi-year La Nina, 24 La Nina prediction and multi-year La Nina occurrences have been affected by this. Johnson proposed that delayed occurrences of the atmospheric and oceanic coupling in weak El Nino events, so 14, 15, 18, 19, were linked to the tendency of SST zonal gradient between the western and central equatorial Pacific that has strengthened significantly since 1979. The strengthened zonal, so this is talking about strengthening from 79 all the way to now, so regime shift in the middle is not related to this on the western side. Strengthened zonal gradient produces an atmospheric response that opposes the response to elevated EPSSTs and inhibits the expected onset of central tropical Pacific deep convection during 2014-15, and 2018-19 events. Through climate model experiments, Lim et al. Also suggested that the strength of extreme El Nino events such as 82, 83, and 97, 98, and 2015, 16 was reduced with a strengthened zonal contrast as a result of reduced thermocline feedback and weakened rainfall wind SST coupling over the tropical East Pacific, which is also consistent with the simple model results of Hu et al. However, the relative importance of the zonal SSTA gradient and the amplitude of the SSTA is yet to be robustly quantified, robustly and quantitatively estimated due to the fact that just 4 cases of uncoupled El Nino have been observed. So sampling issue plus these are kind of retrofitting the explanations, and they are consistent, but doesn't mean they are final. So they have to be confirmed with model experiments and so on. In this regard, we note that another common factor of the 4 uncoupled warming events is their late start. All 4 events started in August to October as measured by SST exceeding 0.5 degrees C for the first time, as we saw already. This late onset corresponds to a climatologically well-established cold tongue. So you have strong upwelling happening in June, July, August, sometimes into September. So these are occurring at the end of the upwelling season. And the largest seasonal mean zonal SST gradient on the equator occurs during that time. So west is where you have a strong front and the gradient. These conditions could also limit the eastward extension of deep convection, confining enhanced precipitation to the far western Pacific south of the equator, thus limiting the coupling of the atmosphere and ocean in the tropical Central Pacific and Eastern Pacific. I didn't show figure 4, but you could see that in there. So if the strong seasonal cycle persists and El Nino is trying to do something, the argument is that seasonality is going to affect the El Nino and limit it to the Western Central Pacific and not allow coupled Beck-this feedback and atmospheric response to happen. Just to conclude, challenges for prediction. Currently, most of the operational climate prediction centers, such as CPC, IRI, International Research Institute for Climate and Society at Columbia University, and Australian Bureau of Meteorology, rely on some oceanic indices as the underpinning of for ENSO forecasts and monitoring. In reality, these simple SSTA indices sometimes fail to reflect the coupling between the atmosphere and ocean. So if you just track Nino 3 index, it may say, yes, El Nino happened, but coupling may not have happened. And this is important because predicting them is harder. Plus, the teleconnections are different because the convection doesn't shift as much and they start late. Furthermore, ocean warming in the central and eastern tropical Pacific has different impacts on the extratropics for cases with and without atmosphere-ocean coupling, which makes it necessary to distinguish coupled from uncoupled warming events to determine the likely skill in forecasting far-field teleconnections. Just to jump to conclusions, lastly, it is still a challenge to accurately describe atmospheric and oceanic coupling processes associated with ENSO in reanalysis and in climate forecast systems. Once the model run happens, to diagnose coupling is not always easy. For example, Kumar and Hu found large differences among reanalysis for the intensity and the spatial structure of ocean atmosphere feedback terms involving precipitation, surface wind stress, and ocean surface heat fluxes associated with ENSO. For climate forecast models, tropical convection and ENSO evolution are sensitive to the parameterization of atmospheric convection, as always. Zhu et al. Noted a substantial sensitivity of the SST prediction skill to different convection schemes, particularly over the eastern tropical Pacific. They argued that the convection scheme having the highest skill simulates stronger and more realistic coupled feedback related to ENSO, thus accurately representing the different mechanisms responsible for different flavors of ENSO and their global impacts in climate models represents a significant challenge for climate prediction. So the key question is whether these are indeed related to global warming or some part of internal variability. And if it is related to global warming and stratification changes, which we invoked before in cloud feedbacks and 23 El Nino and so on, then we have to really be careful because we are saying many things. We are saying global warming is happening, the warming pattern is kind of cooling in the east and warming in the west, and then we are saying stratification changes and so impacts are happening. There is also a regime shift overlapping with this east-west gradient trend, and We are saying uncoupled ensos may be happening. We are saying multi-year La Niñas may be becoming more common. CP ensos may be becoming more common, which is related to this uncoupled El Niños, and so on. So even though there is no robust single answer, we keep on adding this may be happening, that may be happening. So you have to be always careful because, as this paper admits, sampling issue is serious. There are very few samples of all of these things, but we are still trying to squeeze some response out of the system. Okay, so let's leave it there.